Next week, we'll focus on the concepts of energy transmission and distribution, because in the near future, the way that we transmit and distribute electricity will look quite different from how we do it today. We'll talk about the concept of distributed energy that's gaining traction in the marketplace and the technologies that are connected to the grid that are seeing advancements. We're leading to a smarter grid, a better grid, a more optimized grid, and we call that the smart grid. We'll introduce technical and economic concepts about the grid and explore its role in the future energy landscape. So in this first section of the lecture, we'll focus in on energy transmission and distribution and concentrate on electricity and how it gets from the power plant to the consumer. You'll also watch a video on the so-called smart grid, or the grid of the future, that needs to be developed in one way or another to ensure that electricity flows in a reliable, secure, and efficient manner. I'll remind you that this week we're focusing on different sections from chapter 16 and 17. It's section 16, 1, 2, and 4, and section 17, 4, 5, and 6. So we'll start off by talking about electricity and understanding electricity as an energy carrier. Of course, energy can be carried in other forms. Water flowing, the water carries energy. Even natural gas entering a furnace, that natural gas comes with its own chemical potential energy. And of course, the photons that are incident on the Earth's surface are also carrying energy. These are natural forms of energy that are found and manipulated by humans oftentimes and converted into other forms. Now, one thing that we can do is convert some of these forms of energy directly into electricity. Electricity it is not found naturally. Maybe the exception to that would be except lightning. So lightning carries free electrons. But otherwise, electricity is something that humans have learned how to induce and use it for our own purposes. So in contrast to getting heat from burning wood or getting direct mechanical work from burning gasoline, right? Electricity is an energy carrier that we often need to flow it to a particular end use in order to use it. Benjamin Franklin in 1750 discovered electricity as a carrier in this way. He discovered that electrons flow when there's a difference in electric charge, otherwise known as voltage, in a material. And then in 1786 or so, Alessandro Volta invented a battery to take advantage of this idea that if you separate electric charge and you have a gradient of electric charge, you can actually induce current to flow. George Ohm discovered that voltage is equal to current times resistance, or V equals IR, which was also important to understand, so that by 1820, some really important discoveries were made about electricity. That electric currents in wires generate a magnetic field, and then also that wires carrying current in a magnetic field have forces on them. And all of this was very important to get us to this point where we could design an electric generator. So about that time when those discoveries were made, Michael Faraday invented the electric motor, which was then improved about 20 years later by figuring out that time-varying current in one pair of wires induces current in a second wire. And if a magnet is moved near a closed loop of wires, then current is induced in those wires. And so again, this is the basis, the physical basis for an electric generator, and is the theory of electromagnetic induction. So again, just to make sure you fully grasp this, because we take these electric generators, we attach them to turbines, we get that motion, right? The moving current, the moving magnets that we can actually put on the electric generator. That these two concepts were critical to being able to make electric generators. How the motion of a conductor in a magnetic field generates electricity. It generates an electric voltage across that conductor. And then 2, the passage of current through the conductor in a magnetic field produces a force on that conductor that results in rotational motion. So again, these 2 concepts being the basis for an electric generators. First, DC electric generators were constructed and later turned into AC. And generally, the presence or the discovery of this electromagnetic theory and development of electric generators has certainly changed the lives across the world. The Thomas Edison taking advantage of the use of electricity to create and invent the light bulb, certainly with some help from other scientists before his time. That happened in 1880, which again really impacted and disrupted our lives in positive ways. Early power plants that used electric generators were hydroelectric, so they harnessed the energy being carried by flowing water to then attach that to turn blades that are attached then to some kind of electric generator. And then that evolved to the development of coal or gas-fired power plants that used steam to turn the blades of the turbine and generate electricity. And that then evolved into centralized utilities as we know them today. So by 1930, most cities in the US and Europe had electricity transmission and then distribution. So what we need to understand is that when an electric generator is employed, the primary energy must be consumed in a heat engine to produce work. We've talked about this over a few weeks or so, that using a Rankine or a Brayton cycle, we can convert some fraction of that heat to work that is then transmitted as electric energy. Now, electricity is characterized by a number of different attributes: voltage, current, frequency, also phase angle. The suitability of these properties, the suitability of the electricity that's generated depends on how these properties meet the demand needs of a particular application. So for example, if all we're trying to do is run electrons through a current to generate heat, we probably don't care too much about the attributes of voltage, current, frequency, or phase angle. But for a power electronics type application, we might care a lot and require very tight control of these attributes. And so it's very important to understand that when electricity is delivered to an end application, control of these attributes is usually critical to ensure high power quality for those applications that need it most. Another important point here is that due to inefficiencies across transmission lines and across the distribution systems, about 11% of electricity is lost before it actually reaches the consumer. So how does the electricity generation ecosystem look today? We typically have centralized generation. We have centralized utilities. As you know, 25% of primary energy consumption in a typical industrialized country is electricity. In the US, it happens to be higher, 40%. And again, a very high majority of that electricity in the US comes from this centralized generation, these power plants. But varying customer demands can create problems for utilities, because what utilities are trying to do is instantaneously match supply to daily, hourly, and even shorter variations in demand. So we have to think of electricity being continually and instantaneously balanced between supply and the demand. And that's because we don't typically use energy storage solutions, so that if the power plant makes too much energy, we can store it. We don't have that kind of utility scale solutions for storage yet, and as a result, we have to make sure there's this constant balance between that supply and also the demand. Of course, we never want our power plants to make too little electricity, because somebody, be it the residences, the businesses, or the industry, will then suffer and not get the electricity that they need. If we make too little electricity, that can also lead to outages for many of these different industries. So just a quick aside here, because I want to make sure we're talking about energy transmission with a focus on electricity. I want you to understand too, and kind of put in context, how other energy carriers are transmitted. So pipelines are used for oil and gas, also coal slurries. Trucks and trains and ships are typically used for coal and oil and uranium. Liquid natural gas, because it's not a liquid at room temperature, has to be refrigerated in tankers, which cause the prices to go up. But then electricity, again, is carried in wires. And just think about the comparison between that transmission through wires of electricity compared to the transmission of these other types of energy resources, that the costs associated with transmitting in wires is so significantly lower and simpler than all of the costs associated with these other forms of energy sources. Now, some of these forms of energy sources are necessary in order to lead to the production of electricity, right? So they're not necessarily replacing one versus the other. But it's one of the reasons why electricity is so attractive and ultimately so low cost, because we can generate the electricity in a centralized location using some kind of fossil fuel typically, and then transmit that electricity, at least if we don't have to go long distances, for relatively low cost. So once that electricity is transmitted along high voltage lines, it gets to a distribution system. And that distribution system then carries the electricity to consumers. But what I want to point out here is that some of that is changing, that there's an interest and a growing interest in distributed generation, or DG, or also called distributed energy resources, DER. This is an alternative to that idea of centralized generation. When we have distributed energy resources, a distributed generation like solar power plants, and they could be small ones sitting on the roof of a house, or they can be larger power plants, let's say 1 megawatt, that's serving a campus. There are typically shorter distances between those power generators and the end uses. That leads to lower losses. There are smaller scale of these generation plants within the system, so you have a lot of little plants rather than one big centralized one. Sometimes they can include conventional fossil fuel-based generation, such as something called combined heat and power. So think of them as small power plants that are using fossil fuels to generate electricity, taking advantage of heating needs as well, and doing this on a relatively small scale, distributed throughout a population. And then because we have smaller scale power being generated, we can use smaller scale energy storage solutions, which are much more attractive from a technological standpoint, but also from an economical standpoint too, at least based on the current technologies available in the industry today. So I just want to end by mentioning the benefits of distributed energy, distributed generation, understanding that distributed generation might be good because we could use more renewables for this kind of application, but also there are other benefits, such as being able to meet some kind of emergency capacity need, being able to meet growing capacity needs. So rather than building a whole new power plant because a certain population is growing and has bigger energy needs, perhaps we can meet those needs without that huge capital investment of a power plant, and by using distributed energy resources along that population. Also, security might be a concern. By having distributed sources, we're sort of delocalizing and diversifying our energy resources, and as a result, that benefits security. And I think distributed generation has become particularly attractive to consumers for various reasons. They might be because of environmental reasons, but a lot of consumers point to the idea about avoiding power outages. Oftentimes, consumers want to avoid being at the mercy of the utility and potential power outages that might occur. Some of you might remember the power outage in 2003. I remember exactly where I was at that time when the lights went out. And that resulted from a large surge in power that was believed to have started in Ohio. And because of an alarm in a control room malfunction, there was a propagation of error that really ended up influencing the grid across many, many states. Because the grid is very interconnected and dependent on different locations around the grid, dependent on each other, a distributed generation approach helps mitigate any problems due to power outage and due to perhaps a domino effect that might happen in an interconnected grid. Smart grid might also help us better manage the grid, better optimize electricity usage, better deal with the fact that it may be too hard to exactly, continuously, and instantaneously meet supply and demand. And so a smart grid of some kind is certainly in our future. So now I'd like you to watch a video on the smart grid.